Well, good morning. So today we're going to go over a lot of the rules of probability that are not really complicated things, but we want to make sure we have absolute certainty. There can't be gray area when you're doing calculations. We want to know that we got stuff absolutely correct. So the first question I'm going to ask you, real simple question. I'm going to roll a pair of dice. I would like to know what is the probability of my outcome, my sum of my two dice, being a multiple of either 4 or 6. So find the probability the sum is a multiple of 4 or 6. Now, that's a fairly simple thing. So what I did was I produced the dice roll chart for you, reproduce all of the probabilities of the various sums. Now, which sums are multiples of 4 or 6? Well, let's see. The multiples of 4 would be what? Would be those guys. It would also be those guys. How about that guy? Would those be all the multiples of 4? Everybody? 4s, 8s, 12s. How about the multiples of 6? That would be these guys right here. So if I was calculating, and I just go over there, I'm counting all of these outcomes. So clearly I'm going to have that value, that value, that value, that value. So if I count them up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Clearly there's 14 outcomes. 3, 5, 5, 1. Okay, so do we all agree the probability is 14 over 36? Everybody okay with that? I'm rolling the dice. What's the probability my outcome is either a multiple of 4 or a multiple of 6? Okay, it's an or. I mean, I can't be a multiple of 4 and be a multiple of 6 unless it's that one. So this is the answer. So now the question is, how could I have done this conveniently, easily? I don't really want to have to do this every time I answer a question or produce all of this information. Now, this is easy enough. Where did that number come from? Well, what about the probability? And I'll just keep it simple. What is the probability of rolling a multiple of 4? Actually, I'm going to write it this way. Multiple of 4. Sorry. What's the probability of rolling a multiple of 4? Will it be this, this, this? So I believe we circled 9 rolls that were multiples of 4. So there's no question that's 9 over 36. What's the probability that a roll is a multiple of 6? Well, now which ones are multiple of 6? 6 and 12 are multiples of 6. And that would be 5 plus 1 or 6 out of 36. Okay. So if I took the multiples of 4, which was 9 out of 36, I took the multiples of 6, which is 6 out of 36, that doesn't add up to 14 out of 36. Does anybody see a problem? I mean, if I just calculated these independently and added them up, that wouldn't have given us the right answer. We know that's the right answer because we wrote them all down. Why don't these agree? Anybody want to guess? Or not guess, give me a reason.
12 is repeated.
Wait, say it again. Say it again.
12 is repeated in both.
Oh, I counted this particular outcome in both of these. Does everybody agree with that? That you're absolutely correct. I counted one of the outcomes twice because the number 12 is a multiple of 4, but the number 12 is also a multiple of 6, which gives us kind of a quandary. And that kind of sets us up for the first really good formula we're going to go over. So I'm going to erase this. All right.
Could you please return to the, like, what does it mean, multiple of 4 on 6?
A multiple of 4 would be every multiple of 4, 4, 8, 12.
Yeah, no, what you wrote down there, multiple of 4 on 6. What does it mean?
The probability of a multiple of 4 we calculated was 9/36. The probability of a multiple of 6 we calculated was 6/36.
Oh, it's 4 or 6. Okay, I see.
But those values, the original question was or, those values didn't add up. And as John pointed out, it's because we counted one of the outcomes twice. So I have events A and B. The probability of A or B, that's what we just did. Question, is it the probability of A plus the probability of B? That's the question. Because that's what we just did, and we found that didn't quite work. So let me draw you a picture. We're going to create a formula that is always true. Okay, there's my A, there's my B. If I count the number of elements in A, I will get all of this. If I count the number of elements in B, I will get all of this. But the problem is this guy right here, which is called the what? What do we call that piece?
Intersection.
That's the intersection. I counted it twice. So the easiest way of doing this is if I counted it twice, then I'm going to subtract it out. So this is the formula. And by the way, instead of or, what's another symbol I could use that would be more mathy that would go along with this? Rather than the word or,
A
Might-
plus B.
might-
rather than the word or, there's only one word in math that translates, only one. You've been using it all along. There's absolutely one word in all mathematics that translates as or. I'll give you a hint, it's not that guy.
Union.
Union. Yeah, that should have been a slam dunk. The probability of the union is the probability of the individual guys minus the probability of the intersection, because the intersection got counted in both. And that's a problem. And here's part of the reason that's a problem. If I'm not mindful of that, I could have a situation where my probability exceeds 1 if I'm not careful. So this is an absolute formula, across the board formula. So let's see how that a really simple case. Okay. I went out recently and I conducted a poll of San Diegans, and let's say A is the event A is that a person goes to the beach. These are San Diegans. Let's say that B is that the person loves hockey. Okay. And then we went out and we measured all San Diegans, and we found out, oh, and by the way, what would A intersect B be in that case? What would A intersect be? Who's in that group?
He goes to the beach and loves hockey.
Yeah, beach loving hockey players or hockey loving beachgoers. Okay, everybody agree with that? We'll just say beach and hockey. Of course, we know that's a huge percentage of San Diegans right there. Now, we went out and measured, and we found out that we were told the probability that somebody in San Diego, okay, probably somebody in San Diego is a beachgoer, let's say was 0.8. Let's say we found out the probability that somebody in San Diego is a big hockey fan, let's say was 0.4. And let's say that the people in San Diego that were beach-going hockey fans was 0.3. Okay, these are things that were measured, given to us. So my question is, what is the probability a person, what is the probability a person goes to the beach or loves hockey? What's the probability a person goes to the beach or loves hockey? So I'm actually asking this question right here. Well, you'd say, well, duh, the answer is clearly going to be 0.8 plus 0.4. And what's wrong with that answer besides the fact that it's wrong? Tell me something way bigger than the fact that it's an incorrect number. Why is that a really terrible answer?
The number is also over 1.
The number is bigger than 1. That's it's about as impossible as it gets. The only thing worse than getting a number bigger than 1 would be getting a negative number for probability. That doesn't make sense. I can't have a probability greater than 1. So in my picture, here's the easiest way to rectify it in the picture. And here's the mistake a lot of us make. Well, shouldn't I put 0.8 and 0.4? Oh, but I have an intersection, I'll put 0.3. There, now just add all of them up. I think that just got even worse, didn't it? Because I'm asking you for the union. If it were the union, now I'm up to 1.5. A lot of people try to use the picture and go like, that picture just made it way worse because the picture is incorrect. What's the only part of this picture that's correct? There's only one part that's correct. Anybody want to tell me? Given those 3 numbers, there's only one part of this that's correct. Stare at it for a minute. See, right now we have 1.1 in A, we have 0.7 in B. That's not correct. That's correct, but that's not. Oh, how much is right here?
0.5.
0.5. 80% of the people in San Diego fall in circle A, but I've already got 30% of the people falling in the intersections. Oh, that means that outside the intersection must be another 0.5. So then over here, outside the intersection must be a 0.1. Now, when I look at that picture, it is absolutely correct. So what I had to do here was subtract the 0.3, and that gives me 0.9, which is what my picture now says. So if I said, given nothing but this information, okay, the probability a San Diegan goes to the beach is 0.8. The probability a San Diegan loves hockey is 0.4. And the probability a person goes to the beach and loves hockey is 0.3. Now you can tell me what's the probability a person goes to the beach or loves hockey. What's the probability a person goes to the beach and doesn't love hockey? That's the 0.5. What's the probability a person loves hockey but doesn't go to the beach? That would be the 0.1. What's the probability a person doesn't love hockey and doesn't go to the beach? Boy, this is a really boring person. You don't want to invite them over. But what's the probability a person isn't hockey-ish or beach-ish? Where would I find that number?
It's 1 minus what we found before.
Would you agree it's that number right there? Why is that? Because that's everything else. Oh, that would involve complement. We'll figure out how to work that in. So any question I could ask you now, you could answer because we have enough information. Here's where a Venn diagram is very helpful, but I got to fill in the numbers correctly. So the formula we've developed is the formula for union. It's actually a really, really simple formula. Union can always be calculated. Intersection cannot. And one of the most common fallacies in statistics and probability is that people try to calculate the intersection because they think they have a formula. You cannot calculate an intersection. You can only count an intersection. You have to either be told what the intersection is, or you could physically count the intersection. But there's no mathematical formula for calculating an intersection. And I'm always amazed because I've been teaching this kind of stuff for years, and I'll have a high percentage of people say, oh yeah, I saw this online. I saw this in a textbook. I saw this in a class. No, that's not even a possibility because that formula doesn't exist. No, you have to be told the intersection, or you have to have the ability to count the intersection. There is no such thing as a formula for intersection calculation, but there is a formula for calculating the union, and it involves the value of the intersection is in this case. So Sergey mentioned complement. Now, so we want to look at that. So first thing is, let's throw a what if at you. What if I'm looking at a picture where I have no intersection? Okay, what if I'm looking at a picture where A intersect B technically is the empty set? Then the probability of A intersect B would be 0. So I want to introduce some language that you may be familiar with, but it's a context kind of related thing. If we are talking about sets, this is not probability, I just have sets. One set might be a class roster for one of my classes. The other set might be my neighbors, a list of names. There's probably nobody that's on both of those lists. If two sets have no intersection, we say the sets are disjoint. So when you're using sets, disjoint sets have an empty intersection. Okay, nothing to do with probability, that's just sets, that's the vocab. But now that we're talking about probability and counting, now think of A and B as events. Oh, all of the outcomes that showed up in A. For example, let's go back to the dice roll. I want all of the outcomes that are multiples of 4, and I want all of the outcomes that are multiples of 5. Are there any outcomes that are both multiples of 4 and 5 with the dice roll? That's a fairly simple answer. If I'm rolling the dice and adding up the sum, we know we can get a multiple of 4, you know, 4, an 8, a 12. I can get multiples of 5, that would be 5 or 10. Are there any outcomes that are multiples of both 4 and 5 at the same time?
It's 2 dices? No.
No. So there are no outcomes that are, if I said 4 or 5, you'd find the probability of 4 and you'd simply add it to the probability of 5 because the intersection would be the empty set. So when you're talking about events that have no common outcomes, it's equivalent to talking about two sets that are disjoint. So if events A and B have no common outcomes, it's the same situation, but we use different vocabulary because we're now talking about probability. We're talking about outcomes of an experiment as opposed to just a couple of different lists. We say that A and B are, and the term is mutually exclusive. Now, some of you may have heard that. Mutually exclusive events is the equivalent of disjoint sets. So why do we use different words? Because an event is a list of outcomes of a probability experiment. A set is just a set. It has nothing to do with probability. I have a class roster, that's a set. There's no probability associated with that question. Oh, okay, so I have two sets that have nothing in common, the sets are disjoint. But if I list all of the outcomes of an experiment and I say, here's this event and all of its outcomes, here's another event and all of its outcomes, they have no common outcomes, the events are mutually exclusive. Therefore, when I'm calculating the probability of the union of the two, the or, there's nothing to subtract because the intersection would be empty. Okay, that makes life a lot easier. So in this case, probability of A plus probability of B minus the probability of the intersection, there'd be nothing to calculate. So that's our favorite one because it's really, really easy. But I never assume an empty intersection. I would have to either be told that or I'd have to be able to figure that out on my own. Okay, so now what about complements? Whether I'm talking about sets or I'm talking about events, in this case, we'll talk about events. So I have the event A and I have the event A complement. Okay, if I have the event A complement, and by the way, some textbooks they'll use an A bar, some textbooks they'll use a squiggle. I'll just use the C. A and A complement. So if I have event A, I have event A complement. What do I know about a union A complement? What do I know about a intersect A complement? These are events now. We're not using sets, so we want to use the analogous terms that we would use with events. So first of all, let's do the easy one. What's a intersect A complement?
0.
Would it be an empty set?
Yeah, empty set and 0 are not the same thing. Yeah. First of all, a set doesn't have a value, so it'd be the empty set. The probability would be 0. Yeah, let's make sure we got the difference. So something and its complement have no intersection. That is critical. But when I take the union of something and its complement, what do I always get?
0.
The union of something and its complement? First of all, intersections and unions do not produce numerical values ever.
Would it be the universe?
In sets, we'd call it the universe. That's exactly it. But now we're talking about events. So there was a different word we used when we're talking about events. Does anybody remember what it was? It's actually 2 words. They both start with S. So now we're talking probability experiments. So instead of universe, what's the
Sample space.
Sample space. And often it's just S for sample space. The sample space of a probability experiment is exactly the same thing as the universe when I'm talking about sets. We use different vocab so that we know what it is we're actually talking about, because in a probability experiment, ultimately, we're going to be measuring things, counting things, representing things with numerical values. If you just have sets, there's no numerical value. I just have a list of things. But now we're saying, what's the probability of an outcome? Oh, okay. So that's why we use different language, just so we make sure that we understand. In this case, we're talking about a probability experiment. So sample space. So I have all my outcomes. I have all the not outcomes. Now I have everything. So here's a really, really cool fact that is one of the most useful facts at all. The probability of a complement. The probability of a complement is equal to, well, first of all, what is the probability of a union a complement? What must that be if it's the whole sample space?
1.
That would have to be 1. But since there's no intersection, doesn't this also mean that the probability of A plus the probability of A complement equals 1? Because there's no intersection. I don't have to say minus the intersection, because there's nothing there. Do you agree with that statement? So that means this is always true. It turns out that is one of the most useful facts in all of probability. And I'll tell you why it's useful. I want to calculate the probability of something happening, but maybe that thing is really big, and maybe that thing is most of the cases. Well, if the complement is smaller than the original event, then it's absolutely always easier to find the probability of the complement. That's an absolute. If the complement is smaller than what it is you're asked for, find the complement and subtract it from 1. I'll give you a really simple example. Let's go back to the dice rolls. I would like you to find the probability. I'm going to roll the dice and I'm going to do it one time. I'd like you to tell me what's the probability that my outcome is less than 12. Now, what are the outcomes that are less than 12? 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10 or 11. So I find all of those probabilities. I add up all of those probabilities. And that's correct. What's the only probability I didn't include? If I said I want the outcome to be less than 12. What's the only probability that I didn't include in that question?
12.
12. And what's the probability of getting a 12? Well, this 1 out of 36. Oh, so what's my final answer then? 1 minus 1 out of 36. Wouldn't that be a lot easier than calculating all of those other probabilities and then adding them? Yeah. So if I said, what's the probability of, generally when you're thinking things like inequalities, I've got all of these outcomes. Well, what am I not counting? That might be really small. Let me count that and subtract it from 1. That's absolute. Always true. The probability of a complement might be easier to calculate than the probability of the original thing. I'm not saying it is. It might be. It is often easier. Okay. Now, with that, we get one of the coolest rules for probability that you'll ever see. One of the absolute coolest rules. Okay. I'm going to show you one. All right. Let's say that there's a slot machine, at a local casino that you like to visit. And over time, it's been measured because you had people measuring things. They actually can keep these kind of statistics. That slot machine has been played tens of thousands of times, maybe 1 million times. And you found out that the probability of winning at any given try, the probability of winning, let's say, is 0.001. Okay, that's 1 out of 1,000. By the way, just like the roll of the dice or the flip of a coin, every time you do it, it's brand new. The one thing about probability that a lot of people mistakenly think is like, when I flip that coin and I've got like 3 heads in a row, the coin is starting to think, oh, we need to lean the other way, land on a tail, because the coin has a little computer chip inside of it that says I need to, or not. In other words, every time you flip a coin, it's brand new. It starts all over. It's 50-50 every time you do it. Every time you roll the dice, it starts all over again. There's no record keeping of the die or record keeping of the coin. That slot machine, every time you play it, it starts over. Okay, it doesn't keep a record. Oh, well, you know, we had a winner last week. Let's go a few more days before we have another winner. No, it doesn't work that way. There's no thinking. So if this is the probability, this is the probability every single time you play. So here's the question. Okay, let's say Sergey had a day off and he decides to go hang out all day at the slot machine, and he's got the big old bucket of quarters, you know, and he's just going to keep feeding them into the slot machine, and he's going to play over and over again, hundreds of times, maybe 1,000 times. Is it likely he might win sometime in there? Maybe. Heck, is it likely he might win more than once even? Sure. Okay. So let's say Sergey plays 1,000 times. You play 1,000 times. Sergey's going to play 1,000 times. Okay. Yeah. That's, you know, you have time. You have all day. I want to find the probability of winning at least once. What does at least once mean? What's at least once?
One or more.
One or more. So it could be 5 times. It could be 367 times. It's one or more. Now, if I said, what's the probability that he wins exactly 3 times or 5 times or 11 times? That probability is actually difficult to calculate. We're going to learn how to do that one much later. But the probability of a specific outcome is actually quite difficult. But I just said, what's the probability he wins at least once? That means what's the probability he wins once or twice or 3 times or 4 times, all the way up to 1,000 times. You're going, that's crazy. That would take me forever. Wait a minute, at least once. What's the only other outcome?
None.
Never at all, none. Oh, so maybe I calculate the probability that he never wins and do what with that number? What if
Subtract it from 1.
subtract it from 1? Ah, so I'm teaching you the probability. This is called the probability of at least once. That is what the title of this piece is. A lot of textbooks will have this as an entire section. This is the probability of at least once. Why? Because the probability never changed. So what we're first going to do is figure out, okay, what is the probability of not winning, which is the same as losing? What's the probability? If the probability of winning is 0.001, what is the probability of not winning? Anybody?
0.999.
So how about 0.999? Yeah, not a lot of options here. You either win or you don't. If that's the probability of winning, then that's the probability of losing or not winning. There's not a third option there. So to never win means you lose every time. Now, yesterday we talked about the matching and multiplication principle. Every time I play, the probability of winning is 0.001. So if I said, what's the probability I win on my first try? You say 001. What's the probability I win 2 times in a row? Then it'd be 0.001 times 0.001. What's the probability I win 1,000 times in a row? Then it'd be 0.001 raised to the 1,000th power. Pretty small number. But what's the probability I lose? 999. What's the probability I lose again? 999 times 999. What's the probability of losing 1,000 times? Anybody? What would be the probability of losing all 1,000 times?
0.999 to the 1,000.
To the 1,000th power. Exactly. That is the probability that I just lost 1,000 times in a row. By the way, I mean, my probability of winning is not very good. So every time I play, I'm probably going to lose. But that number is not 1. I'm not guaranteed I'm going to lose 1,000 times in a row. That number is not 1. It's smaller than 1. So now what is the probability of winning at least once? Well, if this is the probability of losing every time, Isn't that the complement of winning at least once? Winning at least once, the complement is winning 0 times. Winning 0 times is the same as losing every time. So what would this be? The probability of winning at least once would be 1 minus. And this is how you calculate the probability of at least once. The probability of at least once is always 1 minus the probability of none. But that goes back to what we've done earlier. So let me grab my calculator. Let's see if we can calculate this bad boy. Okay, so when I do 1 minus, now it's very interesting. The probability that I win at least once, you might be, whoops, what did I just do? Hold on a second. Sorry, I set my calculator on the computer, bad idea. 6323. Now, this is the time I do want to use a decimal because I could write a terminating decimal down. It's actually possible. Exactly how many decimal places does this number have? Does anybody know exactly how many? This is something you learned as little kids and you probably forgot. I have a 3 decimal place number raised to the 1,000th power. Exactly how many decimal places does this have? 3 decimals raised to the 1,000th power. Oh, come on, take a guess.
6
3,000.
or 3,000.
It has exactly, it's a terminating decimal with exactly 3,000 decimal places. Do you think we really care what decimal place 467 is? Mostly, probably the first decimal place is the one that really matters. So it is common, if you've ever read statistics, you would know this also. It is common when reporting probabilities as decimals. I have a 3,000 decimal place number. I'm not going to write out 3,000 decimal places. That's absurd. When reporting probability as decimals, you did a calculation and you got to round it off. 4 decimal places is actually considered the norm. If you've had statistics, you know that because you go back and forth with your Z tables, they're always reported as 4 decimals. It's just convenient. There's nothing about 4 that's critical. You know, what if I want 3? What if I want 7? No, it's just 4 is kind of the industry standard. And if you've had stats, you were usually required to give exactly 4 every time you did a calculation. That's not important. But look at that number. That number is almost 2/3. I'm going to play this ridiculously impossible slot machine. It has a 1 out of 1,000 chance of winning, but I'm going to play it 1,000 times. My probability of winning at least once, I don't know, that's pretty darn good. So that means if I did this enough times, by the way, can I play it enough times that probability is ever 1? No. But as I increase the exponent here, this number is going to increase. It'll never be 1 though. What if I played 1,000,000 times? What if I played 1,000,000,000 times? Yeah, but the fact that there's always a probability that you're going to lose is never a guarantee that you're going to win. But clearly, if I do this enough times, my probability goes up and up and up and up. Now, still 0, 0, 1 every time I play. But if I said I'm going to play it 1,000 times, then when I walk away, hey, I won a few times. Great. You know, that's kind of the expectation. So the probability of at least once. Now, it's not a difficult thing at all. It's because the probability with the 0, 0, 1 never changed. So if we were doing a dice roll, a coin flip, you know, a slot machine, something where the probability does not change, right? I can actually always do this calculation. So the probability of at least once is always, I look at the complement, and the complement of at least once is not at all. It's a fairly simple notion from that standpoint. Now, the next thing I want to talk about is a particular type of situation. Now, with sampling, okay, I did these things at the graduate level at San Diego State, and this is always one of these kind of gray areas. When we're talking about sampling, and whether it be sampling from a population of people or trying to sample from the animal kingdom or even plants, I'm trying to do samples. You can't look at every single thing. I'm trying to do, you know, maybe I'm collecting information about mountain lions in San Diego. Well, I can't get every mountain lion in San Diego. I have to sample the mountain lions that I can find. I want to do something about people. Okay, I sample the people because there's just too many people to try to measure everybody. So when you're doing sampling And it's always called random sampling. You don't say, I think I'll choose that person. No, that's not how it works. That there's always the possibility that something can show up in your sample more than once. If I'm just randomly sampling, I hire a whole bunch of you to just go out and randomly ask people questions all throughout San Diego. Well, it's possible the same person may get asked more than once, particularly by different samplers. Now, is this a good thing? Is it a bad thing? Is this just part of the nature of things? Well, that's what we have to decide ahead of time usually. So most of the time in real life sampling, if somebody gets asked a second time, we don't care. It's just sheer random chance. We don't worry about that. When you're doing animals and you're doing, you've got your grid of the county, and you're going to randomly select different parts of the county, just little regions of grids. Well, and then count the number of animals in that grid. Well, one of the animals could have moved over to a different grid. You don't worry about that, because there's always the possibility you missed some along the way as well. So now if I'm doing sampling, then there's two concepts when you're doing sampling. You sample with replacement. You sample without replacement. What that means is I have a finite number of things to select from. Again, it could be animals, could be people, could be cards. When I make my selection, do I keep the selection out? If I'm sampling people and I've asked you that question, do I now exclude you from further samples? It's not about right or wrong, but it affects the calculations. So let's keep it really simple. We have a deck of cards. A standard deck has 52 cards, okay? And we know some of the cards have numbers 2 through 10. We have aces, we have jack, king, queen. So we have, those are called face cards. So we have these kind of things. So let's just say I'm going to select 3 cards. I want to find the probability they are all numbers. The numbers would be 2, 3, 4, 5, 6, 7, 8, 9, or 10. Those are the numbered cards. Then there's ace, jack, queen, king are the other cards. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers. Now there's also suits, right? Everybody understand there's suits, spades, diamonds, hearts, clubs. So exactly how many number cards are there in a deck of cards? If there's 9 different numbers and 4 different suits, exactly how many of the cards in a deck are numbered? Anybody want to guess? It's not a guess.
36.
36, 9 times 4. Okay, so there are 36 numbered cards. So I want to select 3 cards. Now, it kind of matters how I do this. I've got, the old, I shuffle the deck, I flay out the cards. You're looking at the back of the cards and I say, the old pick a card, any card. Are you picking 3 cards at one time and then looking at them? Are you picking 1 card, looking at it, setting it down, picking a card, looking at it, setting it down, picking a card, looking at it, setting it down? That's almost the same thing. Or are you looking at a card, putting it back, and then I reshuffle? Now you're going to select again. And then you put it back, I reshuffle. Does everyone see that completely changes things if I do that? So with replacement versus without replacement will affect this answer. So in this situation here, if I said I'm going to do it with replacement, that means I'm going to look at the card, determine is it a number or is it not a number? Okay, great. And now I'm going to put the card back in. So the same card has the option of being selected again. So 36 out of 52 is the probability that I select a number, and that will stay the probability, and that will stay the probability. Okay, so this is the first case. With replacement means that it starts over every single time. I have the exact same 52 cards. I have the exact same 36 cards that have numbers, and I'm going to select them. So I do that on my calculator. And I raise that to the 3rd power. My answer is 729 over 2197. Okay, that's roughly about a third. In fact, it's really close to a third. Now, if I do it without replacement, is the answer different? All right, I pick a card, any card. You picked your card. It was either a number or it wasn't. Well, what's the probability it's a number? Well, it's still 36 over 52. So now, what's the probability your next card is a number if the first card was a number?
35 over 51, maybe?
Why? Why is it 35 over 51?
Because you took one card?
Because there's one less card and there's one less number. So what's the probability the next one's also a number? What's the probability the next one is also a number?
34 over 50.
Yep. So does everyone see that completely changes things? If I've already got a numbered card and I pull it out, there's not as many numbered cards and there's not as many cards. So my denominator changed also. So let me do this. This is where you want to use your fraction key, by the way. And then 34 over 50. And my answer is different answer. This one's 21 over 65. It's just a little bit less though. If you compare the decimals, the second answer is a little less likely because every time I pick a card, this number's going to keep going down just a little bit. Now, the idea that if a card, if I've selected a card, I looked at it, it's a numbered card, I set it aside. There are now less cards, there are less numbered cards. That affects my probability. Might this be useful if you were a card player knowing this? This type of mathematics, might that be useful? You see, we're going to play cards at my house today. You know, I just have one deck of cards and maybe four of us are going to sit around a table and play poker or play blackjack or play some game, some card game.
You will want to be the
illegal
last
for you to
person.
use that.
You're kind of paying attention to the cards as they're being played, because as cards are being played, we set them aside before we start the next hand. Or
counting.
you see what people are playing. And what is that called? Someone said?
Card counting, right?
It's called card counting. By the way,
Which is
can you do that at a casino?
No.
No. It's considered cheating. And it is dealt with generally very severely, and not because they're going to call the police. Oh no. It's not a good thing. Yeah, if you're a card counter and you get caught, you're in, yeah. I don't want to go there. I've heard too many horror stories and I've actually seen it. I've seen news reports on TV. You know, they did it was a 60 Minutes a number of years ago. They did a special on a guy. It was a card counter. And he was really, really good. And he was at a major casino in Las Vegas or Atlantic City. I can't remember. And he did literally like the fake nose mustache. He was trying to be, you know, incognito, although he kind of stuck like sore thumb. And he's winning hand over fist because he's really good at this. And at one point, you see the manager come over and then they covered up the camera and they found the guy the next day in a dumpster, broken in half. No joke. He was immediately terminated because they realized what he was doing and he was cleaning up. He was winning a ridiculous amount of money and it was all being on camera. You know, they're doing this for the special. And so yeah. And the funny thing is that no one really got very upset, which I thought was more than creepy. But the thing is, it's considered cheating if you're actually doing it. So they don't take, but if you're a card player and you're just paying attention, right? Paying attention, you go, well, you know, all the aces have been played. There are no more aces or there are no more kings. You're aware of that. That may affect your decision-making and probably is a good idea. So the concept of without replacement means that every time something happens, it has an effect on the future stuff. And that's really, really important to be aware of. So there's a very simple example. With replacement is easy calculations because nothing changes. So in the last case where we did the slot machine, every time you played, it started over. Okay, there was no change in the probability. But the situation where if it's a without replacement, then every time you do something, the probability does change. Cards are probably the easiest illustration of this concept. Okay. Now, the last thing I want to cover today, this is kind of a cool one. And it's actually one of the simpler ones. All right. Now, I've got a bunch of people in a room here, and like in my department, they like to celebrate birthdays. Every single month we celebrate birthdays. You know, there'll be an email go out of all the people whose birthdays, so, you know, people can sign cards and things like that. And then some of the people will actually make nice baked goods, you know, and just sort of honor and celebrate those people who had birthdays that month. Okay. Now, it's possible that we have some months that are celebrated by more than one person. That's a piece of cake. How many people would you have to have together, do you suppose, before you know there's a month with more than one birthday? You know, if I got 3 people in a room, they could all be in different months, couldn't they? How many
So
people do you think we'd need to have together before we know there's a month with multiple birthdays?
13,
Why 13?
because if you have 12, then each one can fall into a separate month. And then
Exactly.
one
So
month,
the first 12 people could all be different months, but that 13th person would have to go into one of those months. Now, to me, this is borderline, oh, duh, mathematics. It's like, yeah, of course that's it. But this is actually an extremely powerful theorem slash principle. It's called the Pigeonhole Principle, which is a silly name for what we're talking about. But the Pigeonhole Principle is very, very, very old. And it goes something like this. In New York City, on a lot of rooftops, there will be these like little birdhouses. I mean, I've seen them. It's kind of crazy. Birdhouses, maybe with hundreds and hundreds of perches. Okay. Now, the pigeons will come and they'll roost there, and you'll feed them, and people like doing that kind of stuff. But let's say there's, 200 little. The pigeonhole would be the little individual birdhouse. There'd be a stick coming out and there's a hole. They will roost on the stick or maybe climb into the hole. That's like his little home. Okay, that's what it's called, a pigeonhole. So I've got 200 of these. But if I have 201 pigeons, there has to be at least one pigeonhole with more than one pigeon. Does that make perfect sense? Same as the birthday you just said. If I have more pigeons than pigeonholes, then there must be at least one pigeonhole that has at least one, or excuse me, that at least 2 pigeons. So I can use this fact to help me make certain conclusions, because a lot of times we make a mistake. Let's think calendar year. Let's leave out leap year for a moment. If in a calendar year, if I said, what's the, how many people do I have to guarantee that somebody's got the same birthday? How many people would I have to guarantee somebody has the same birthday? What do you think?
366.
Yeah, 366. So if I say I got 1,000 people in a room, I got 1,000 people in a room. Must there be a day in the year that at least 2 people have the same birthday, or maybe even 3 people have the same birthday?
yeah.
Well, let's see. I used 365, and if I had 730 people, I could have them evenly spread out, couldn't I? And every single day of the year has exactly 2 people. But the 731st person would now require there's at least one day with 3 people. Does that make sense? So if I had 1,000 people in a room, there's at least one day, actually probably several, there's at least one day that has 3 people with the same birthday. Now, I'm not saying what day of the year that is. I don't know what that day is. But the Pigeonhole Principle kind of like elapsed now. Okay, so if I start counting by 365s, if I have 3,650 people, it's possible that every day of the year could have exactly 10 people. But the 3,651st person would now guarantee there's at least one day with 11 people. The same notion. Does that make sense? It's a fairly simple notion. Now, don't confuse that with the probability. I said, how many do I have to guarantee? But if I said, I've got, let's go simple here. There are 10 people. You don't know any of their birthdays. If I want to find the probability at least 2 share a birthday, Well, that's tricky. So do I go, okay, what's the probability they share January 1st? What's the probability they share January 2nd? No, because it's not what day of the year they share. I have 10 people. What's the probability to share the same birthday? Now, when I was teaching stats, I used to do this problem every semester. What I would do is I'd write down the months of the year. And then I would just say, now January, holler out if you're born in January, just holler out your date. And 3, 17, 30. And then, okay, February, I wouldn't look at what they're saying. And then we do this. And if somebody, if the same number came up twice in that month, that means that 2 people shared the same birthday. And I would do this, and I'd have a class of 40 people, and I would tell the students, I bet you at least 2 of you have the same birthday. How? There's only 40 people, there's 365 days. But the probabilities are a little bit deceiving. So I'm going to show you how to do this calculation, and you will be surprised maybe by the results. To find the probability that at least 2 people have the same birthday, what's the complement that at least 2 people share the same birthday?
Everybody share different birthdays.
That everybody has different birthdays. Yeah. So either everybody has a different birthday. You don't say, well, one person has the same birthday as themselves. No, that means everybody has a different birthday. Oh, at least 2 people share the same birthday, or nobody has the same birthday. That would be the complement. So let's calculate nobody has the same birthday. And then like we did before, subtract that result from 1. So if there's one person, the probability that they have the same birthday as themselves, well, that seems kind of silly. But now the second person, what's the probability they have a different birthday than the first person? Well, wouldn't that be 364? So if I have 2 people in a room, here's the probability they do not share a birthday. Okay. Now,
Pretty good odds.
third, yeah, pretty good probability on that one. They don't share the same birthday. Now, what's the next person? And the next person, oh, I wanted you to do this for 10 people. So what would the last quotient be? What would the last one be?
355.
Careful. That's the second person, that's the third person. So
Oh, yeah. Sorry.
56. Because I'm counting backwards. Now, this is the answer. I don't want to do it. What if I did this for 100? That'd take me forever. Oh, but wait a minute. We know a way of calculating that numerator. What's the numerator? What is 365 times 364 times 363? Isn't that a permutation? Remember, think factorials. Oh, if I put a 355 factorial over a 355 factorial, the top is permutation, 365, choose 10. We just did that yesterday. Oh, okay. So this is 365 factorial over 355 factorial. That makes sense. This is the probability. So let's do this. So, oops, sorry. 365 fat fingers. 365 permutation 10 divided by 365 raised to the 10th power. Now, this is not the answer. This is the probability that nobody has the same birthday. Okay, this is approximately the probability no 2 people have the same birthday. So what's the probability that at least 2 have the same birthday? What would I do with that? My answer is 1 minus this. So the answer to the question, let me just do it. The answer to the question, 1169. Okay. Approximately this. The probability, if I have 10 people in a room, the probability at least 2 share the same birthday, I'd say, that's actually kind of big. Now, you can have some fun with this. You're going to a party. Let's say you're going to a party, you don't know anybody. You're going to a wedding reception, and you look around the room, count how many people are there. You see 50 people there. You see 40 people there. This would be a good time to place a bet. Say, I bet you some amount of money that at least 2 people here have the same birthday, and I don't know any of them. Didn't do this ahead of time. As long as you can prove that you don't know any of them. And they'd say, seriously, there's 50 people here and you're going to bet me $100 that at least 2 people have the same birthday. I'm taking it because there's 365 birthdays in the year. All right. Let's say there's 50 people in the room. let's have fun with this one. Let's say there are 50 people in the room. Now, I don't know if your calculator will be able to do this. I might have to do this on my titanium. That's 50. And let's just go ahead and say the answer we want is 1 minus this anyway. So let's just go ahead and directly do that calculation, shall we? Let's see. I don't know if my calculator can do this. Oh, you know what? I don't think I can. Hold on. Let me pull out my titanium. I'm looking at the numbers might be just a little bit too big. Hold on. All right, gee. Battery's dying. You know what? My battery on my titanium just, I forgot to, is dying. Let me see if I can do this. I don't think we can do this. All right, let me make it a little bit smaller. See, we'll do that one. Okay, let me make that instead. Let me see if I can do 40. I'm doing this with a cheap calculator. All right, so I'll do 30. I know I can do 30. I wanted to do 50. You have to have a pretty powerful calculator. Why? Because that number is way bigger than 10 to the 100th power. And unless you want to enter fractions, I don't want to enter fractions. If you enter the fraction, you can do this. It takes a really long time. So we're going to do it for 30 people. Okay. I know we can do this. We can do this. So I'm going to do 365 P30 divided by 65 raised to the 30th. All right, now that's a simple calculation. I just did that really fast on my calculator. The answer is 0.7063. Okay, hold the phone. I got 30 people in a room, 30 strangers. I don't know any of them. The probability at least 2 of them have the same birthday is around 0.7. Does that seem a little high to you? That 30 people in a room, the probability is bigger than 0.7 that at least 2 have the same birthday? Yeah, that's why I said the numbers might confound you. That seems silly, but it's true. And every time I add an additional person, that probability goes up. Now, when will the probability reach 1? When can I absolute guarantee that at least 2 people have the same birthday?
At
When more people than,
365 or 6.
At 366. And you say, well, how come I can guarantee it at 366? Because we're doing 1 minus, agreed? If I continue doing this, won't at some point, that's 365 people, by the way. And what's 366 people? Do you see from a calculation standpoint? 1 person, 2 people, 3 people, 365 people, 366 people, because there's no days left. If we actually did it from a calculation standpoint, the 366th person, that probability that they're different from everyone else would now be 0, which is why my answer would be exactly 1. But the fact is that with 30 people, it's better than 0.7. So this, by the way, we have a really clever name for this problem historically in mathematics. Does anybody know what this is actually called? This is in every stats book and it's called the birthday problem.
And there are 2 types of years. Some years have 1 day more and one.
Yeah, I said, let's leave out leap year because that just confuses the heck out of people. I'm sorry if you were born on leap year because that means you only get birthdays every 4 years as it is. I don't want to, stomp on those people. Now, here's a question I have for you. How many people would it take before the probability exceeds 0.5? Because let's face it, okay, if you're a gambler, okay, and you and I all day long, we're going to flip coins. If I win, I'll, you pay me $1. If you win, I'll pay you $1. We're just going to flip the coin all day long. At the end of the day, we're probably exactly the same, right? We're going to basically break even because of the probability. That's not a very exciting game. But what if we played a game and my probability of winning exceeded 0.5? I'd play that game in a heartbeat if we're going to bet the same amount of money, because it means in the long run, I'm going to win more. That's just how it works mathematically. So at what point would the probability that at least 2 people have the same birthday exceed 0.5? We did it for 10 people and the probability was around 0.11. We did it for 30 people and the probability is 0.7. Anybody want to make a guess what they think around? It's actually not a hard calculation. Anybody want to guess? You may have seen this before. You guys are not very adventurous today.
I would say like 22.
Not bad. At 23 people, this is the probability at 23 people that at least 2 have the same birthday. Just barely. 22 is still just under. At 23 people, the probability exceeds 0.5. That's why I said you walk into a room with a whole bunch of people and you look around going, there's more than 23 people here. So therefore, the probability that at least 2 have the same birthday is better than 0.5. Now, if you're a betting person, that's the type of thing you're going to do, right? That's pretty much what it comes down to. You see 100 people in a room, that probability is way, way past 0.9. I mean, yes, it's still possible that nobody has the same birthday, but the probability is ridiculously high. It kind of defies common logic at first. So pigeonhole principle is basically I use up all the pigeonholes and each additional guarantees something now. That's different than the calculation of the probability. Okay, I want to make sure we understand. So if I have less than 365 people in a room, I can calculate the probability that at least 2 have the same birthday. If there's more than 365 people in the room, then I'm guaranteed at least 2 people have the same birthday by the pigeonhole principle. So the pigeonhole principle only applies if I've exceeded the number possible there. Okay. So in the birthday case, so let's use months. We have about 40 people in this class. Is there a month? Can you guarantee me there's a month that has at least 4 people with the same birthday? Is there a month with 4 birthdays? Can you guarantee me with 40 people in our class that there's a month with 4 birthdays or more? Can you guarantee that? Think about it for a minute.
I don't think so.
Well, you said this before. If I have exactly 12 people, it's possible they could be spread out each month. If I have exactly
36. People, yeah, you will have 1 month. Yeah.
If I have 36 people in a room, is it possible that I've spread it out and I got 3, 3, 3, 3, 3 across the board?
Yeah.
That's possible. In other words, I can't guarantee you 4. But the moment I have the 37th person, now there must be a pigeonhole that has at least 4 pigeons. See, that's the pigeonhole principle as well. So with 40 people in a room, can you guarantee me there's a month with at least 4 people? Yes, you can. And how? Because 40 divided by 12 exceeds 3. So that remainder is going to be where the 4th person is. But at 36 people, you can't guarantee a 4th. You can guarantee 3, but you can't guarantee the 4th until, again, they get that extra pigeon shows up. All right. So today is some of the funnest, coolest stuff and the least challenging from a calculation standpoint. Actually, I'm not going to stop recording quite yet because I want to talk about the exam now. We have a party tomorrow morning, starting a little bit before 8 o'clock, and you're encouraged to show up. And again, like all math parties, you're encouraged to show off and stretch your math stuff. I will be sending you the exam about 7:35, 7:40-ish right there, with the intent on starting at 7:45, just to give you an extra 15 minutes. Not that you need it, but an extra 15 minutes means you're less likely to stress out over time. I will send you the Zoom link and the exam. And again, I'll send an email reminder later. You're going to either print the exam or you're going to write the problems down on white paper. Some of you love using graph paper with really, really dark grid, but it makes it really hard to read. So please use white paper. Don't use anything that has lines on it, because when you translate it to me, the lines are darker when you send them to me than they are with what you're looking at. And sometimes it's harder to read. The exam covers starting at section 4.7. In other words, where the first exam ends, that's the first exam. Now the second exam begins with the material from June 17th. First exam was 8 lectures. Second exam is also 8 lectures. There are no questions directly from the first exam. Is there logic you learned? Well, yeah, things, complements and negations, we're still doing certain things, but no questions that were directly from the first exam. So if you've reviewed the practice tests and you've gone through all your quizzes, you've seen pretty much every version of the test. You may bring a 3x5 card, both sides, with theorems, formulas, definitions that we've covered in this class. There's vocab that some of you may not be familiar with. For example, what does it mean to be reflexive, symmetric, and transitive? These may be words that you're not familiar with, so you can write down the definitions. What you can't do is give yourself an instruction manual of how to do a problem or put down examples, because at that point it's open book. The test is not open book, but theorems, formulas, definitions, because in writing them down, you're just going to reinforce them and solidify them and probably never end up even looking at them. Is there calculations on this? Well, the only calculations really are like the Euclidean algorithm stuff with it, which is arithmetic. So I would strongly suggest you have a cheap calculator with a fraction key. That's all you need. You don't need anything more powerful than that. As we're starting to do probabilities and things, still a cheap calculator with permutations and factorials and things like that, that's all you're ever going to need in this course. You don't need anything high powered or fancy. You just want to be able to do the arithmetic without having to do it in your head, or off to the side or something like that. On this exam, you will have more questions than you have to do. So there will be a section of the exam where you're going to be able to choose. You always like that kind of thing. So the rule of thumb is always the same. As you're working through, do enough problems. Don't do extra, do enough. When you get to the end, proofread. If there's still time on the clock, try the extra credit. I threw an extra credit on there. Now, if there's still time on the clock, go back to the part where you had choices and do an extra one. That's called insurance. Okay. Hold on, I gotta turn that off.
Call from RICA.
Okay. It is always a good idea to do insurance because you don't, if I say here's 10 questions, you've got to do, hold on. If I say here's 10 questions, you've got to do 5 of them. Doing 6 of them is very wise. Doing all 10 of them, no, because the ones you did at the end, right, they're probably not that great because there's a reason you skipped them. But doing an extra problem is always wise. It's insurance. It can't hurt, can only help. Try not to leave anything blank along the way. Now, if you truly don't know how to do it, don't dwell on it. Don't take a lot of time because no problem is a deal breaker. There's no problem that is worth, 10% of the test kind of thing. So if you dwell on something small and insignificant, yeah, that can affect the time you have, and then you might be rushing. So if you show up, you're prepared, you've tried everything, you already know what I'm going to ask you. You just don't know exactly what numbers I'm going to use, but you know exactly the nature of questions. So let's take a short break at this point.